All right, here in section 4.1, we're going to be reviewing matrices from Algebra 2. We're going to be talking about what a matrix is and performing some operations on matrices, namely matrix addition, subtraction, and scalar multiplication. We're also going to transpose a matrix, okay? All right, so recall, a matrix is just an array of numbers. An array is like an arrangement of numbers. Matrices are really good for organizing large amounts of data, numerical data, okay? You're typically going to represent a matrix with a capital letter. So here we have matrix A, and this matrix has 6 total elements, and we arrange the elements into rows and columns. Okay, so this particular matrix has 2 rows. The rows are horizontal. Here would be row 1. This would be row 2. And then your columns are vertical. That's column 1, column 2, column 3. Every matrix has a set of dimensions associated with it. Sometimes it's referred to as the order of the matrix. And you would give that as the number of rows times the number of columns. So for this matrix A, I would say it has 2 rows and 3 columns, so its dimension or order would be 2 by 3. Okay. One thing to notice is that when you multiply those 2 numbers together, you get 6, which is the number of total elements in the matrix. All right, now if I want to represent one specific element within the matrix, I can use subscript notation with lowercase letters. So if we're dealing with matrix A, if you see lowercase a with a subscript next to it, that's talking about an element within matrix A, a specific element. So here I want the element that is in the first row and third column. Okay, so I look here. Here's the first row. Here's the third column. You can see the overlap is -1. Okay. All right, now let's start performing some operations on matrices and doing some different things with them. So first here, we're going to be setting 2 matrices equal to each other. For them to be equal, they have to have the same dimensions. So in this example, I have a 2 by 2 matrix, 2 rows, 2 columns, equal to another 2 by 2 matrix. And when 2 matrices are equal, that means their corresponding elements are equal. So that would mean x plus 4 in the first row, first column is equal to element 3, which is in the first row, first column of the second matrix. Therefore, x plus 4 is equal to 3, x is equal to -1. Similarly, 2y minus 6 would have to equal 12 then, since they're both in the second row, first column. All right, solving that, 2y would equal 18, y would equal 9. And similarly, 2z minus 4, that would have to equal 2. Or 2z equals 6, so z equals 3. Okay, example 3. We have more of the same thing. I have a matrix equation that I'm trying to solve here. Now, at first glance, you might think these matrices do not have the same dimensions. So the first matrix, I would say, has 2 rows and 1 column. Well, technically, so does the second matrix. This is also 2 by 1. Why? Because this is all considered one element of the matrix, and so is this. So really, there's only 1 column here, okay? So I'm going to be able to set y equal to 3x minus 2. All right, now I can't solve that by itself since there's 2 variables in there. But notice if I set the other 2 elements equal to each other, I've created a system. Okay, and of course I can solve that system algebraically. This one would be perfect for substitution. So I'm going to say 3 is equal to 2 times, I'll substitute 3x minus 2 in. And now I'll be able to solve this for x. So I'll distribute. Seven is equal to 7x, x equals 1. And now I'll substitute 1 in for x in that first equation. I'll end up with 3 minus 2, or 1. So I could say the solution here, I could write it as an ordered pair, is 1, 1. All right, now let's start performing some different operations. Here I have matrix A and matrix B. They're both 3 by 3 matrices. And I would like to add them together first. Okay, so they have to have the same dimensions in order to be able to add, which they do. And the resulting matrix will be a 3 by 3 as well. And don't overcomplicate this. You're just going to add the corresponding elements. So, for example, I'm going to add 1 with 2. That'll give me 3. Work my way across. 3 plus 4 will give me 7. Negative 5 plus 1 will give me negative 4. Now add the second row elements together. Negative 4 plus 5 is 1. 5 plus 0 is 5. 0 plus negative 2 is negative 2. And now add the third row elements together. 4 added with negative 10 is negative 6. Negative 8 added with negative 1 is negative 9. And 9 added with 4 is 13. Next, we're asked to find 3 times matrix A. Well, 3 here is known as a scalar, or scalar multiple. So this is scalar multiplication. And again, don't overcomplicate this. All we need to do here is multiply each element of matrix A by 3. Okay, so first row, if I do that, I'll get a 3, a 9, a negative 15. If I multiply the second row elements of matrix A by 3, I get negative 12, 15, and 0. And the third row elements by 3, I get a 12, negative 24, and 27. All right, next, this might be new for you. Here we have, it looks like matrix A is being raised to the power of t. We would read that as the transpose of matrix A, or A transpose. And all that really means is we are to interchange the rows and the columns. So the first row elements of matrix A turn into the first column elements of the transpose. Okay, so this would equal, I'm going to take these first row elements and I'm going to make them into my first column. Okay, 1, 3, negative 5. Notice how the order I place them in. I work from left to right, and then when I place them as a column, I'm working top to bottom. Okay? All right, I'll take the second row elements and make them my second column, negative 4, 5, 0. And then my third row elements, I will make my third column, 4, negative 8, and 9. All right, lastly, we're being asked to take 3 times matrix A and subtract it by matrix B. Well, I've already found 3A, that's the matrix in green. So I just need to take those elements and subtract them by the elements of matrix B now. Okay, so if I take 3, I subtract it from 2, of course I get a 1, right? If I take 9 subtracted from 4, I get a 5. If I take negative 15, I subtract it from 1, or by 1, I get negative 16. Okay. Now work with the second row elements of matrix 3A there. So negative 12 subtracted by 5, that'll be negative 17. 15 subtracted by 0 is 15. 0 subtracted by negative 2, careful here, that's going to be positive 2, right? 0 minus negative 2 turns into 0 plus 2. Use the third row elements, 12 minus negative 10, it's 12 plus 10, so 22. Negative 24 minus negative 1, that really turns to negative 24 plus 1, or negative 23. And 27 minus 4 turns into 23. Okay. All right, lastly, just really quickly want to talk about some properties associated with these matrix operations. So in these properties, I'm going to use the letters A, B, and C to represent 3 matrices. And for these properties to work, they're all going to have the same dimensions. And I'll also be using a lowercase c to represent a scalar, okay? So first is the commutative property of addition works for 2 matrices of the same dimensions. So matrix A added with matrix B would be the same as matrix B added with matrix A, okay? Associative property of addition works as well. If I add 3 matrices together, I have to do 2 at a time, right? So maybe I'm going to add B and C together first and then take the result and add it to A. Well, that would be no different if I maybe added A and B first and then took the result and added it with C. All right, the distributive property holds true for scalar multiplication of matrices. So if I'm taking 2 matrices, adding them together that have the same dimensions, and then I multiply that by a scalar of matrix, a scalar of C, then that would be equivalent to had I multiplied the 2 matrices by that scalar first and then added the results together. Okay?